Hello my dear students. In the model 4 design of a three-phase induction motor, one of the most important question it is output equation of a three-phase induction motor it is. Okay, let me start with the derivation of this output equation. See here, the design of a three-phase induction motor. In the previous session we have already discussed about the basic concepts about the induction motor itself here. So in this case, in this today's session we'll discuss on the output equation. So what exactly the output equation? The output equation, it is nothing but which relates the output of the machine, nothing but the output kVA with its main dimensions. The main dimensions means which are those? One, it is diameter of the stator bore, and one more will be length of a armature core length it is. Getting my point? So the output equation which gives the relationship between the output of the machines with its main dimensions, or in other words we can also say that the output equation is the mathematical expression which gives the relationship between the various physical as well as the electrical parameters of the electrical machines here. So before starting this derivation, let's have a nomenclature of this. So what are the things we are going to be considering this derivation? The first thing it is EPH. EPH, it is nothing but the EMF induced per phase, that will be expressed in terms of what? Volts here. The second one it is IPH. It is nothing but the current per phase in amperes. Then third one it is TPH. Nothing but number of turns per phase. That is the reason it is represented as a TPH. Then fourth one it is flux. The flux per pole in the air gap here. P, it is nothing but the number of poles. Then KW, it is nothing but winding factor. Don't get confused with KW here. In case of a design of a transformer, the KW, it indicates the window space factor. But in this case of a designing part of a three-phase induction motor, that KW represents what? Winding factor. Don't get confused. Okay. Then B average, it is nothing but average flux density in the air gap. So AC, it is nothing but ampere conductors per meter. This B average, it is also going to be called it as what? A specific magnetic loading. I hope this is, everyone should be knowing about this one. Average flux density means that is specific magnetic loading, and AC, it is nothing but the ampere conductors. In the name only it is a representation. A, small a for ampere, C represents the conductors here. So it is nothing but the specific electric loading, and D, it is nothing but the armature diameter, and L, it is nothing but the stator core length it is, and NS, it is nothing but synchronous speed in RPS. Don't get confused. Capital NS means synchronous speed, in RPM it is. And that small ns, it is synchronous speed in RPS, revolution per second. And the efficiency, eta, full load efficiency, and the cos phi, it is full load power factor it is. Then finally one more, it is tau, nothing but the pole pitch it is. Pole pitch in the sense that there are two poles will be there. One, it is a north pole as well as the south pole. That area we are going to be considering here, that pi into D divided by P. So this is very important thing it is. Tau, it is nothing but the pole pitch, that will be given by what? Pi D divided by P here. And next thing it is, see here, let us consider one. Let us consider an M phase machine. We don't know how many number of phases are there. Let us consider the M phase machine with the usual notations here. So efficiency will be given by, all of you familiar with the efficiency equation, output divided by input. It will give the total efficiency of the machines here. So the output will be expressed in what? In kilowatt it is. So this output will be represented what? Q here, capital Q. It is representation for the output, and it will be in the what? Kilowatt it is there. From this equation I can write output will be equal to, from this equation I can write output, right? So this will be, output will be equal to input into efficiency. Call this equation as a 1 here. So next thing it is, from this equation only, first I want to know what is the input here. The input to the motor means that will be M VPH IPH into cos phi into 10 raised to minus 3 here. So see here, so what is the input? Input means input kVA rating of this machine. kVA means kilovolt ampere it is there. So that is the reason volts VPH, IPH, that is the power factor, into 10 raised to minus 3. So this will be the input to the motor here. So M indicates what? This is the number of phases what I told you. Now we are deriving the equation for the 3-phase induction motor here. Then how many phases will be there? M will be equal to 3 here. So that is the reason M I take it as a 3. Then what will be the input now? Instead of this M, I will substitute 3 here. 3 VPH IPH into cos pi into 10 raised to minus 3 kilowatt here. kW. Getting? So this is the input. So next thing it is, we know that the supply voltage for phase, that will also be nearly equal to the EMF induced for phase. It is there, EPH. Then what is the EMF induced in an induction motor? What is the formula? I think everyone will be familiar with this. EMF induced in the induction motors itself. See here. So this EPH will be equal to 4.44 F pi into TPH into kW. Keep it in a mind. F, it is nothing but the frequency. This will be the flux, and this will be the number of turns per phase, and kW, it is nothing but the winding factor. So this derivation you have already studied. The EMF induced in induction motors you have already studied in the 4th sem itself. That is the reason directly I have taken here. So this EPH will be equal to what? 4.44 F pi TPH into kW. Then what I will do now? So this things it is, where we know the formula for a synchronous speed here. Ns is equal to 120 F divided by P here. From this equation, I can write the formula for frequency. The frequency F will be given by what? P/Ns divided by 120. This is in case with respect to what? When we synchronous speed, when we are considered in terms of RPM here. But the small Ns will represent the synchronous speed in RPS. It is revolution per second. It is nothing but 60. 60 into 2. It will give the 120, but it is per second I am taking here. That is P/Ns divided by 2 it will be there. Getting? F will be equal to P/Ns divided by 2. So next, this equation EPH, what it is there? Instead of this F, I can substitute this P/Ns divided by 2 here. Then 4.44 into P/Ns divided by 2 into pi into TPH into kW. It is nothing but winding factor here. Then this 2 ones are, and it will be, when we divide it from 2, it will be 2.22. So EPH will be equal to 2.22 P/Ns pi TPH into kW. I hope this one it is clear. Next thing it is, next what I taken here, see here. So one more thing it is, in this EPH only, instead of this TPH, I had substituted Z by 6 here. Why? In the sense that Z, it is nothing but the number of conductors. This number of conductors will be equal to the product of number of phases into the per phase how many conductors will be there. So number of phases means it will be, how many phases are there? 3 phases are there. 3 into how many in each phase? 2 conductors will be there. Nothing but 3 into 2. That is 6 TPH, number of turns per phase. Number of conductors will be equal to 6 TPH it is. From this equation, I can take 6 TPH. TPH will be equal to what? Z divided by 6 here. That only, instead of this TPH, I had substituted Z divided by 6 here. Okay. Then what I told here, the output will be equal to input into efficiency. It is there. So Q, output will be represented by Q. Input, what we got? 3 VPH IPH into cos pi into 10 raised to minus 3 and multiplied with the efficiency only, eta. Okay. So substitute now all these things. So from this equation, Q is equal to 3 VPH, it is nearly equal to what I told here, EPH. EPH means this one, you just substitute here 2.22 P/Ns pi into Z divided by 6 into kW here, into what is remaining, IPH cos pi into 10 raised to minus 3 into efficiency. I had written as it is. Okay. So when we multiply here, 3 into 2.22 means it will be 6.666. So when we divide it by 6 means it will be 1.11. So remaining things, just a modification I had done here. Just see here. Here also P/Ns it is there. Instead of this P/Ns, what I taken here, So random arrangement I had done here. So this P into pi one side I had taken here, into IPH into Z one side I had taken here. Then remaining things will be as it is I had written here. NS into KW into cos pi into 10 raised to minus 3 into efficiency it is there. Okay. We know that what purpose I had done this two at one side means the product of P into pi, it will give what specific magnetic loading it is there. We have a different kinds of loadings what I told. So one it is specific magnetic loading and one more will be specific electric loading here. In the before session we already discussed about the specific magnetic loading, that is represented by average flux density, that will be given by what? P pi divided by pi into D into L it is there. Is it right? So this from that equation only P pi I can write it as a B average into pi DL it is. Call this equation as a 4 here. Then one more loading what I told here, specific electric loading here, that is represented by what? AC. So this will be given by the equation in the previous session already discussed, Iz into Z divided by pi into D here. So now Iz into Z from this equation, Iz into Z, it will be equal to what? AC into pi D. Call this equation as a 4 and 5 here. So now what we got? P pi as well as the Iz into Z here. So in the equation, just you see, observe here, P pi it is there, Iz into Z here. That is the reason I have taken at the one side here. Getting my point? Instead of this P pi, instead of this P pi and to Iz into Z, I will replace, substitute equation 4 and 5 in equation 3 here. Then 1.11 B average pi DL into AC into pi into D. Then then the remaining factors I had written as it is. NS, synchronous speed, winding factor cos phi, and efficiency into 10 raised to minus 3 here. Then see the diagram, see the equation here. 1.11 equation 1.11. So here also 1 pi it is there, here also 1 pi it is there. That is the reason pi square I had written here. So then B average into B average one side I had written here. Here D also there, here also 1 D it is there. Then it will be D square and L is remaining here. L I had written here. Then AC I had written and remaining factors will be same here. NS, KW, cos phi into eta into 10 raised to minus 3 here. Then output Q, so this will be when we multiply 1.11 into pi square. Pi it is the value. What is the value for pi? Just to calculate this one. When we multiplied this pi square with 1.11 means you will get it as 11. So that is the reason B average, AC, KW, efficiency cos pi into 10 raised to minus 3 into D square LNS into KW. Getting my point? One more thing it is, this output will be equal to, so all these terms it is going to be represented as a C naught itself. C naught it is nothing but the output coefficient, and the remaining things will be, I had written same as it is. Getting my point? The product D square L as it is there, NS it is there, KW it is there. Getting my point? The output coefficient of this machine means, in the problem if they had given means, the output coefficient calculation means you should make use of this one, 11 B average AC KW into efficiency into cos pi into 10 raised to minus 3 here. Getting? Suppose one time, sometimes the rating of the induction machines, it will be in terms of horsepower. If they have given induction motor rating in a HP, then output equation will be like a HP into 0.746 divided by efficiency into cos pi it is. Yeah, I hope this is clear with everyone. So this is the output equation of the induction machine here. Okay, thank you.